All right, so here we go. Calorimetry. Yeah, I know, we're stuck with that term, calorimetry. But I want to remind you of a couple things. The first one is heat. We measure heat in an energy unit called a joule. Abbreviation for that is joule. Now you can have kilojoules or microjoules, but typically we just use joules. Yeah, sometimes kilojoules. Anyway, the point is, remember, heat is not the same thing as temperature. Nope, it isn't. Heat is the flow of energy from hot to cold, always from hot to cold. So here's what we're going to be doing in our lab. In our lab, you're going to have a big hunk of metal. And this metal is going to be our system. And we're going to heat up this hunk of metal and to the boiling point of water. And once we get that metal the same temperature as boiling water, we're going to stick it into a calorimeter, and inside the calorimeter will be water. And the water will then be our surroundings. Well, I misspelled that one, didn't I? We'll try it again. Surroundings. Now, whatever heat is inside this metal will leave the system and go into the surroundings, the water. And we can measure the change in temperature of the water. We know the specific heat of water, and we'll be able to calculate the amount of energy the water absorbs. And where does that energy come from? Well, it's going to come from the metal. Because in a perfect world, the law of conservation of energy says energy can't be created or destroyed, only changed. So the amount of heat that the metal, now Q is what we use for quantity of heat. The amount of heat that the metal loses, whenever we have heat lost, we use a negative symbol. That will be directly equal to the amount of heat the water absorbs. Exothermic will be negative, heat lost. Endothermic is positive, heat absorbed. That, in a nutshell, is our lab. The next several slides will take us step by step of how to calculate the specific heat of our metal so we can find the identity of our metal in the lab. In a nutshell, this is our lab. Just take a few minutes and read through this. Where we start with our lab is by measuring the amount of heat the water absorbed. So that'll be Q of the water. And absorption means endothermic. So this will be a positive heat flow. Well, we know that Q is equal to M, the mass of the water, times the specific heat of water, times the change in temperature of water. Or I could write it mass C, the final temperature minus the initial temperature. Well, we know the mass of our water is given up here, so that's 100 grams. We're going to multiply that times the specific heat of liquid water, 4.184, and yes, you do need to know that number, grams times degrees Celsius, times the change in temperature of our water, which went from 24.80 minus 21.31 degrees Celsius. So that means the heat the water absorbed is 1460 joules. Well, how does the heat absorbed by the water compare to the amount of heat lost by the metal? Well, because of the law of conservation of energy, the law of conservation of energy, we know that energy in a perfect world is neither created or destroyed. So we know that the amount of heat that the water absorbed, the absolute value of it, has to be equal to the amount of heat the metal lost. So we just found out that the water absorbed 1460 joules of energy. That means the metal had to lose 1460 joules of energy. We're trying to solve for the specific heat of the metal. Well, that means Q of the metal has to equal the mass of the metal times its specific heat times the change in temperature. We just figured out what Q is. We know what the mass of the metal is. We're trying to solve this guy. Do we know this? Well, the measure of the hot metal, that's probably one of students' hardest things to do. The initial temperature of the hot metal is equal to the boiling water. In a perfect world, of course, that would be 100 degrees Celsius. However, in your lab, you're going to be measuring that water out. You know, it might be 99.8, it might be 97, depends on your thermometer, but as long as you're using the same thermometer for the entire lab, we don't need to calibrate them. We're just going to use the same one. For this lab, we're going to use, for this problem, the initial problem stated it was in boiling water, so we'll use the temperature 100 degrees Celsius. Now, we know that when we put hot metal in cold water, the temperature of the metal will drop. So the final temperature of the water will be exactly the same thing as the final temperature. So here, let me restate that. The final temperature of the metal will be exactly the same thing as the final temperature of the water, because as the metal cools down, the water warms up. So they reach the same final temperature. So in this case, that is 24.80 degrees Celsius. So now we can figure out the change in temperature of the water, or the metal, rather, sorry. It is the change in temperature of the metal that we're after. So just to be clear, the change in temperature of the metal, it went from 100 degrees Celsius down to 24.80 degrees Celsius, which meant we have 74.20 degrees Celsius is the change in temperature of the metal. Please remember this step. Oh, well, probably this one also. We're now ready to calculate the specific heat of the metal. So we know Q of the metal, the mass of the metal. We don't know the specific heat of the metal, and we just figured out the change in temperature. I'm going to rearrange these for C. So C is going to equal the heat of the metal divided by the mass of the metal times the change in temperature. So that's 1460 divided by the mass of the metal, which is 50. I should put units in here, grams. And the change in temperature was 74.2 degrees Celsius. So after punching that into our handy-dandy calculator, we end up 0.394 joules per grams times degrees Celsius. What are we going to do with that? Well, we're going to look it up in a table. Based on this table, I would say our unknown metal was zinc. The last thing you're going to do is calculate your percent error. The percent error is the absolute value of your lab minus the known value, divided by the known value. And then, of course, times 100. Well, our lab value was 0.394, and I'm dropping units, minus the known value was 0.388, divided by 0.388, multiplied times 100, punching it into our handy-dandy calculator gives us a percent error of 1.55%. Not too shabby. I hope your percent error comes out this well. Probably won't, and we'll talk about why that might have happened later. Up next, enthalpy, which is another way of talking about heat.